Welcome. In this lecture, we are going to talk about MATLAB simulation of a practical digital voltage mode control buck converter in continuous conduction mode. So far we have shown lot of experimental demonstration, we have shown the step for implementation, how to do harder like a implementation or prototyping using FPGA. We have shown detail about the Verilog coding, we have presented experimental result. In the previous week, if you recall lecture in week 3, we have presented detail of MATLAB model, how to develop MATLAB model for mixed signal, current mode, fully digital, voltage mode control. Now, the next question is very obvious that after having so much of MATLAB model and experiment, what is the ultimate purpose of modeling and the design? So, unless the model is used to predict, it helps the designer to come up with a unified way where you can justify stability, you can develop strategy for controller design, for various control strategy. Then for a given control strategy, what should be the choice of control parameter? For example, in voltage mode control, what should be the controller gain, digital PID controller gain? So, to ensure, because every time we cannot go to the hardware check, do trial and error, this is a very costly affair and a time consuming affair. In fact, most of the design, one of the main requirement is that saving time. That means, you need to save time in the process of design and iteration, because everybody wants a very fast time to market. So, this lecture is going to consider, can we develop a realistic MATLAB model of a practical buck converter, and then can we check how does the simulation result look like when we operate under the similar condition of a experimental kit, and how do you compare them, are they close enough? If they are close, then before we do actual experimentation, we can use our concept of modeling, we can design, that part will be discussed in the subsequent week. Then we can quickly come to the controller parameter value and then we can plug into the actual hardware. So, that is the objective in this lecture. We want to first consider revisit our digital voltage mode control, some practical detail. We have to develop, we have to consider all the realistic voltage gain, then what are the controller gain, and we want to include this into MATLAB model. So, that MATLAB model now will become more realistic buck converter, but we did the basic simulation with all ideal, even practical, but we have not considered the voltage step down gain, we have not considered the other aspect. So, this time we are going to consider. Then we want to make a comparative simulation and experimental case study, and in the subsequent lecture also we want to show how to plot both simulation and experimental result in a single plot, and then only the comparison will be more useful and meaningful. So, in this lecture, in the few subsequent lecture we have discussed that in the prototype we have considered 1.8 microhenry inductor, 200 microfarad capacitor, and we are going to test the load and reference transient performance under 3.3 volt input, at 3.3 volt input. For load transient we are considering nominal voltage to be 1 volt output, switching frequency is 200 kilohertz, and for load transient we are varying the load resistance between 13.5, which is a continuous resistance, and then we are considering a switch resistance which will be 13.5 in parallel with 0.33. So, this 0.33 resistance is switch resistance. If the Q load is high, this will come in parallel with RC. If Q load is 0, then this will be disconnected. For reference transient, we are going from 1 volt to 1.1 volt. So, let us go detail. So, we are setting the proportional going to be 1.25, integral to be 1.3, derivative to be 8, and we have discussed the hardware implementation in using Verilog. Though we are using 8-bit ADC, but we are discarding 1 bit to avoid any limit cycling effect, and the DPWM resolution is setting 9-bit. So, here it looks like ADC and DPWM resolution is same, but we are not getting very significant problem of limit cycle, but you should choose DPWM resolution much higher than the ADC resolution. So, effective resolution the ADC we are using 9-bit, we can drop one more LSB. Here we are dropping one LSB from 10-bit, resolution become 9-bit. We are using a controller clock of 100 megahertz and voltage gain of 0.27 and the RAM voltage of 2 volt. Now, this is the block that we want to implement into inside the FPGA. This will be sitting there. So, how does this block with our Simulink model? So, if we remember our digital voltage mode control, I think we have discussed in lecture number I believe 26 or 25 or 24. We have multiple lectures in the third week which consider digital voltage mode control. So, if we recall digital voltage mode control, so we are now we have earlier considered V0 directly, but now there is a step down gain and this is Kf is nothing but 0.27. So, that means we are first step we are incorporating the feedback gain and accordingly you have to select the reference voltage, because earlier when there is no feedback gain, the reference voltage should be the one where what exactly you want the output voltage. Now, you have to consider the scaling factor also. Next, so the error voltage after the feedback, this is the feedback. So, here the feedback voltage is here, then we are using an event trigger ADC and this is what similar to this. So, that means we are taking the sample at the rate of the switching frequency. That means we want to capture, you remember if we take this output voltage profile, that means if you take the output voltage profile and if we consider the output voltage sample multiple point and we have discussed that if your switching clock comes here, that means if this is your switching clock come here like this. So, if you capture the output voltage data here, actual data is 1, 2, 3, 4, 5, 6, maybe 6 cycle earlier. Okay, maybe this is not the clock because otherwise it will be too slow. So, this is the point we are capturing. Okay. So, we can capture the data. Where are we capturing? So, here we can introduce a delay, we have discussed this sampling delay can be introduced to make it consistent, and since we are using a pipeline ADC, that means we are considering 6 cycle delay and we are using a 40 megahertz ADC clock, sorry 25 megahertz ADC clock, not 40. So, that is our 8 ADC. So, our total delay for convenience we are taking 6 into 40 nanosecond plus there will be some additional driver delay and all. So, we are taking roughly 100 total, like we are talking about around 350 nanosecond we are taking. So, considering 350 nanosecond is delay. So, our TS is we are using 0.35 microsecond, where our switching period is 5 microsecond. So, this is also captured and the delay is considered here. Next, the controller. Controller, we know how to implement this controller using custom model for Kp, Ki, Kd, that also we have discussed. So, I am not going to repeat it, and we are setting the controller gain according to Kp equal to 1.25 that we have discussed, discrete time controller gain 1.3 and discrete time derivative gain 8. So, we will set those value inside here. Then comparator, we have considered this RAM, but we are not talking about the resolution effect, we can add it, but we have just considered sawtooth RAM. It is varying between 0 to Vm. Vm we have taken approximately 2 volt. Then we have considered this sawtooth dead time, although we are talking about ideal in simulation, we are talking ideal synchronous buck, no dead time is given in the MATLAB, but practically there is a dead time, and that dead time we are giving dead time to be roughly around 60 nanosecond. Okay. So, that is why it is expected there will be slight deviation due to this dead time effect which is not captured. You can do it more realistic simulation, but this is just for understanding how far they are close. Now, we are making a load transient from 70 milliampere to 3.07 ampere at 3.3 volt input. So, this is our experimental result and these are simulation just a current waveform. You can see Here the time division is 20 microsecond. To show consistently, we have also considered 20 microsecond. So that it should visually look like same. Here you can see the voltage resolution, here it is showing, sorry, here it is inductor current. So, 2 ampere, here also if you see the current waveform, here to here also 2 ampere. So, we kept the same scaling. The time also, so this to this, it is like 200 microsecond, which is also consistent with the hardware. You see the current waveform, here we are making just step up, this step up. So, ignore this part, but if you match this to this, they are quite representative. That means, this is the first step. Now, the same condition I am showing separately the output voltage. So, you see the output voltage are also matching quite nicely in terms of the recovery time, like here it is taking like up to this, that means it is taking like 0.1 microsecond roughly. If you take here is 1, 2, 3, 4, 5. So, it is also coming to be 0.21 microsecond. So, that means they are quite representative. Now, we are going to see load step down transient, where the current is now coming from 3.07 to 70 milliampere, 3.07 ampere to 70 milliampere, same condition. So, we have maintained the same time scale. Now, we are showing step down. You see when you apply step down, it is actually taking kind of a 1 cycle delay, it is happening, and you can see this is coming around from here to here roughly around how much, around close to like a 35. So, it is also coming like this. That means, the profile of the inductor current, if you consider up to this point, looks quite representative, and here you see this is 2 ampere, this is 4 ampere, this is also 4 ampere, 2 ampere. So, ripple is also matching, and if you see the output voltage during the step down transient, you can see that current profile we have already matched, the voltage profile is also quite matching. And in the subsequent lecture, we want to actually, because here we have captured as an image, right, we have taken the image of the result, but if we take the .csv file, then we will get a data file, then we can actually compare with the MATLAB data and the experimental data, that we are going to consider in the subsequent lecture, because before that we have to tell the step for taking CSV file and running, and then capturing the signal, then running in your that means post processing, those things we will discuss in the subsequent lecture. But here we are just keeping image of this experimental result and the same of the output voltage. So, here it is the reference transient, and you see interestingly reference transient we are operating at 13.5 ohm resistance, that is my load resistance, and it is undergoing a step up transient from 1 volt to 1.1. So, this is 1 volt to 1.1 volt, this is going here. If you see the current profile, if you look from up to this point, they are quite, because we are only applying step up transient, they are quite similar, quite representative, and if you see the output voltage profile. So, there is an initial kind of slight overshoot, undershoot, and then it is coming. So, it is also same, they are in the same scale, and if you look at the step down reference transient, it is also, it looks similar to that current profile looks quite similar, and if you go to the output voltage profile, that is also matching nicely. So, it means that means I am talking about up to this portion, because we are not applying any step up. It means the experimental and the simulation results, they are matching closely. So, which means we are able to capture the practical aspect, but to get this model we had to struggle, because in the actual we know the inductor value that can be obtained from this current ripple. We have measured the capacitor value, that was quite okay, that was 200 microfarad, although there can be some degradation in the capacitor, but if we ignore that effect, but the challenge was, inductor will also have a DC resistance, right, which is RL. Then switch we have considered the MOSFET, right. That means, if we take a MOSFET, we have to consider the R on. So, RDS on still some information will be available in the data sheet, which was okay, but getting this RL was very difficult, and we had to sort of run multiple case study to come to a close to conclusion that what will be a realistic value of RL, but one can try out identification method. That means, we can do parameter estimation and all, but I am not going to present this parameter estimation method. Here it is more like a iterative way to validate how much is the RL and R on, because R on we are getting around 5 to 10 I think milliohm, but this we are getting close to 30 to almost 40 milliohm for the R on RL for the inductor, the DC resistance of the inductor. So, this was actually a difficult task, because if you cannot match, the damping ratio will be different, because if you go for the output impedance will be heavily or highly affected by the parasitic inductance and resistance, because we know that if you take the high frequency and the low frequency behavior, the inductor high frequency will be, low frequency inductor will be shorted, but its parasitic will come, okay, because the effective R equivalent circuit in the previous lecture, in the previous course NPTEL course, because if we get the equivalent DC model, right. So, the DC equivalent model, we have discussed this DC equivalent model D into V in, then we have to consider this R equivalent, and then it will be R. Okay. So, output voltage will not be simply V 0, it is a DC equivalent circuit, because we need to consider this R equivalent, and this R equivalent is nothing but inductor DCR plus R on. If we consider synchronous buck, and if we consider the on state resistance of the high side and low side MOSFET are same, then you can represent. So, getting these values are very difficult, and that we have used some procedure to do checking by running some DC equivalent case study, and we got some reasonable value for this. And we have discussed the reference transient, both step up and you can do step down. The step down transient also look quite representative if you take the voltage profile also, that we have discussed. So, in summary, we have discussed some digital voltage control practical detail, we have discussed about some realistic MATLAB model, and we have shown some comparative simulation and experimental case study. So, in the subsequent lecture, these results we want to plot in a single graph. That means, we want to take the CSV file of the experimental data, and we also want to capture the data in the MATLAB, and we want to plot in a single graph and show how the current profile looks like. And this will give us, if we get reasonable matching between experimental and the simulation, which we saw it is quite close, then it looks like our models are well enough. Now, you go to the design case study, and after in the subsequent lecture we will go to week, we will go to the design of voltage mode and current mode control, and then that will be used as a tool what should be the parameter of the controller, and then we can design various types of control and we can plug in those value in actual experimentation. So, this process will be very important, the design, and we don't want to validate in the actual experiment. That is it for today. Thank you very much.